Okay. Hello everybody. Welcome back to the third meeting of Inland Empire Math Circle. So today we're going to be talking about just probability in general, more specifically conditional probability, and we'll also be finishing off with a bit of Chameleon. But for now, we're going to be talking about the Monty Hall problem, and let's do a little warm-up question for the Monty Hall problem. So let me just share my screen real quick. Share. All right. So this is our question. Jack has a single sibling. What are the chances that he has a brother? Yeah, so does anyone have an idea as to, yeah, what are the chances he has a brother?
1/2.
Yeah. So like, yeah, why do you think it's 1/2? Oh yeah, by the way, Jack is a boy, by the way.
So he's a single sibling.
Mm-hmm.
So the sibling could either be a boy or a girl. So I think it's 1/2.
Yeah. So now that is a very good way of doing reasoning. However, this is actually incredibly counterintuitive, like so counterintuitive. You can't really intuit it. But if we, why don't we change this problem to a different way? So why don't we change this to something else? So what if John has two children and Jack is one of them? What are the chances that the other child is a boy?
Oh, this is different though, right?
Well, it's actually giving the same information, right? I mean, we're just giving the name of Jack's dad. It's still the same information. You already knew that there were two children. You already knew that Jack was one of them. And yeah, we're still asking what are the chances that the other child, Jack's sibling, is a boy?
Oh, he's so like you can just find the total combinations of two children for
Yeah,
boys and girls.
yeah. So, which is really nice because we have a beautiful diagram right here. So the chances of having two boys, of John having two boys, assuming that is a 50-50 chance, honestly, is 1/4. 1/4 chance of two boys. A 1/4 chance of two girls, and a 1/4 chance of having a boy and then a girl, and a 1/4 chance of having a girl and then a boy. But since we don't really care about order, we can just group these two together. So we know that there's a half chance, if they have two children, we know that there's a half chance that there will be one boy and one girl, right? So, but the thing is that since we know that John already has a boy, which is Jack, then we know that this possibility of having two girls, these possibilities are not possible. It is not possible for Jack to have two girls and also Jack being one of his children if he has two children, right? So that means that we only have these possibilities, right here. And in this case, we know that since there are each of these possibilities is equally likely, right? So that means that we know that um, Jack probably has a sister because there are two possibilities of Jack having a sister. And that means that there's a 2/3 chance that Jack's sibling is a girl and a 1/3 chance that Jack's sibling has a boy.
Oh,
Yeah, so this is actually a very crazy question. It's really hard to intuit, but I think that it is a very nice warm up for the Monty Hall problem. Now, like I just wanted to show just some of these less intuitive things and also a like sort of a way to think about probability, like how you can think about something that is so abstract by sort of making these diagrams, making these things, and actually looking at the way like probability works. All right, so now that we have this sort of interesting warm-up problem, kind of counterintuitive, but this is a sort of nice warm-up for the next thing that we're going to talk about, which is the Monty Hall problem, as Jonathan has mentioned before. So let's have a look at the Monty Hall problem. So the Monty Hall problem, the idea behind the Monty Hall problem is that we have a sort of, I guess, a sort of game show. And the host behind two of these doors is poop. And behind one of the doors is a banana, right? In this case, door 3 had a banana behind it, and door 2 had doors 2 and 1 had poop behind it, right? So what this means is that they're like, does anyone know what the chances of getting a banana are if you just pick a random door? Yeah, Kimmy?
1/3 of getting a banana and then 2/3 of getting a poop.
Yeah, right. So this is actually you know, it's pretty simple. A 1/3 chance of getting a banana, 2/3 chance of getting poop, because there are 2 poops and there's 1 banana, and there are 3 doors in total, right?
Wait, is it always gonna be in the same place?
No, it is not in the same place. This is it's randomized. Oops. It's randomized. So the banana can just appear like in just different places. It just appears differently, right? So yeah, so as you can see here, there is a 33% chance, which is about 1/3. You know, this is like a rough sort of experimental probability. But what is interesting about the Monty Hall problem is that what happens in the Monty Hall problem is that, so first of all, you, like the participant in the game show, you select the door, right? You say you select door number 1. But afterwards, the game show host tells you, oh, actually, there is another door. He opens another door, and behind the other door is poop, right? So, and the question is whether or not you should switch from, say here, door 1 to door 3. Does this boost your chances of getting the banana? Does anyone have an idea as to whether it does and why?
Yeah, so in other words, should you switch your choice or should you stick with the original?
Yeah. Does everyone understand the problem, first of all?
Yes. Is the middle one always gonna be the poop?
The middle one is not always going to be the poop. It's sort of, it's randomized. So
Yeah,
the
but
banana
the
is
one
behind a random.
the one the person opens is always gonna be a poop, right?
Yeah, so the one the host opens is always going to be poop, right? Because the host is not going to open a door with a banana behind it. That would kind of ruin the fun of the show, right? Right. So that's sort of like, you know, obviously he wouldn't open the door with banana behind it. But does anyone have an idea as to whether or not we should switch from door 1 to door 3, or whether we should stay in door 1? Or does it not even matter?
Does it really matter? Because we have like an equal chance.
Yeah,
Think about it
so
again. You have new information now, so the chances could be different.
yeah, it's not necessarily 1/2. Now, like,
Yeah, but like we already know one of them, so one of the other things are gonna be a banana, so it's completely random. We don't know. So there's a 50% chance of us getting any of them.
okay, well then why don't we actually try it out? Let's do some, you know, experiments to see whether or not we should switch. So why don't we just try switching every time and see if there's a 50% chance?
Yes, as you can see, most of the time when you switch, you'll actually get the banana. Of course,
Yeah.
you still get the poop sometimes because it's not guaranteed. So there is a higher chance of getting the banana when we switch. So does anyone have an idea of why that happens? If you guys are stuck, we can start looking at this from the beginning. So first of all, right now, what are the chances that we can get a banana if we click on any of these doors?
So does anyone remember what we discussed before? Like, what are the chances of getting a banana for the first selection?
33.333333.
Yeah, so there's a 1/3 chance. But why don't we think about what it entails if you get a banana first try? So if I select this banana like first try,
Wait,
then
how can you see the banana?
yeah, it's magic. It's magic.
This is just to explain the problem. The actual
Yeah,
game
it's to explain the problem. But if we click on the banana first try, then after the host reveals the other door, what do you think will be on the other side, on the other one that the host did not reveal?
Definitely poop.
Yeah, so if this one gets revealed, then the other door must contain poop because they have a banana here, right? But
That would probably be 100%.
yeah, there's 100% chance if you choose a banana first, then the other door will be poop, right? Yeah, you're getting this pretty quickly. So, but on the other hand, if we click on a piece of poop first, if we got a piece of poop first, then what do you think will happen when the host reveals the other door?
Then the last door would probably be a banana.
Yeah, so the last door, it's not even probably, it has to be a banana, right? Because if we reveal this door, then we see that this poop, the other poop must be revealed, meaning that the other choice must be a banana, right? So if we chose a piece of poop first, then switching will always yield a banana. If we chose a banana first, then switching will always yield poop, right? So yeah, so but remember, does anyone remember what the chances of getting a banana are in like the first place, the first time you choose? What are the chances of getting a banana?
33.3333. I don't know how they calculated this.
But yeah, so there's a 1/3 chance of getting a banana originally. So, and remember how if you get a banana originally, then you must get poop. If you get a poop originally, you must get a banana. So since there's a 2/3 chance of getting poop, then switching means that if you switch, you have a 2/3 chance of getting a banana, which is, as we remember, what we found in this. Does everyone understand that? This is quite complicated, but
Yeah, there's a few different explanations. If you guys don't
yeah.
understand this.
If you have any questions, just feel free to ask. What's funny is that this problem is actually a really hard problem because even some PhD students got this problem wrong. So it's a very hard problem. So feel free to ask any questions if you ask if you have any questions.
Is there like only 3 doors? Because I sometimes watch these and they only have 3 doors.
Yeah, there can always be more doors. The
Yeah,
concept
there can be
is
more
pretty
doors.
much the same.
Yeah, there can be more doors. So as you remember, there is a 2/3 chance of like switching will have a 2/3 chance of yielding a banana. So that means that if you are on a game show and they have this sort of weird contraption, always switch, and you will probably get a banana. I mean, it's not like 100%, but
Wait a minute,
chances
can we
are that you'll
try
get
a
one.
few more times?
Sure, yeah, we can try a few more times if you want to see.
Oh.
Yeah, now of course probability isn't like 100%, right? It's sort of like, yeah, like it's not 100%
Yeah, but you
guaranteed.
have a better chance. Like now it's
yeah.
80%, and that's not really bad.
Yeah. And like, right. And you know how in science, the more trials we do, the more certain we can be. So I would say 18 trials is quite a lot right now. And we can see that, yeah, it's pretty close to sort of what we found before, which is that there's a 2/3 chance, right? 61, 66, I mean, it's decently close, right? It's pretty close. So
You guys want a different explanation for this?
Mhm.
Neo, Loy, Blair, Gavin, you guys all get this? Okay. Cool. So you guys want to move on to a few more doors real quick?
Okay, let's have a look at 4 doors and revealing 2 doors.
Oh God.
Yeah, so Do you guys wanna see like first do the experiment, or do you just wanna just
Could we do
estimate?
reveal four? Could we do 3 doors and reveal 3 doors?
Um,
Does that work?
yeah. Unfortunately, if you do that, then my program will break.
Oh yeah, it'll crash.
Because you know it'll break. If but if we have 4 doors, then we can reveal 2 doors.
Okay.
Yeah. So does anyone have an idea as to what it is, or do you want to just try just experimenting, do the experiment to see?
Experiment.
All right, let's try. So why don't we just select door 1, have a look.
Yo.
Yeah, it's a pretty high chance of getting a banana.
Oh god. 80, 71, 76.
Oh God,
Oh god.
whoops. Yeah, so now we've done 12 trials, and we can see that it is 75%. Does anyone have an idea as to why or what significance that 75% has?
Oh yeah, I get it. Maybe.
It's okay.
So
Yeah,
yeah,
so
we can break down the problem. So first of all, once we first select this, what's the chances of getting the banana on your first selection?
1/4.
yeah, 1/4.
There's 4 doors, right? You have 1/4 chance. So now if there's a 1/4 chance that you got it on your first shot, so what are the chances that the banana is in one of the other 3 doors? So you know that there's a 25% chance of getting the banana if you click on one door, but if you click on, oh no, sorry, the other 2 doors, what is the percent chance that you'll get a banana?
So we already clicked 1 door, 2 doors are revealed.
Oh no,
What are
sorry.
the
If you
chances
just click 2 doors, like from the beginning, if you click on 2 doors, what are the chances you're gonna get a banana?
1/2.
Yeah, right. So you have 2 out of 4. So is
Wait a
there?
minute, maybe a half or maybe even 0, because those two might be both poop.
Oh, yeah, but like in general, it'll be like 1/2, right? So, but so there's a greater chance of getting the banana when you open 2 doors than if you open one, right?
Mm-hmm.
So once you open the first door, and you don't get a, if you once you open the first door and they reveal another 2, that means that what was it? Wait, what? Oh shoot. Once you open the other 2 doors, then there will be, if there was originally a 75% chance of getting the banana in the other 3 doors, then that percentage is compressed down into that one remaining door.
Yeah, so if the banana was not in here, then then there's a 3/4 chance. Like basically, yeah, if the banana was not in here, then the banana must be in the other door that it is revealed. So yeah, I like the idea of concentrating the probability into one door. So it is in fact a 75% chance of getting a banana if you switch in this case. Does everyone understand that?
Well, that's just probably.
Okay.
Just probably. It might be. Because like I'm thinking, if it's 75%, then there's almost no chance of it being uh a poop. So it must be a banana.
Well, the thing about probability is that it's it's like the chance. There's still it could be a banana, but I mean it could be a poop, but it's probably gonna be a banana, right?
Uh-huh.
So like you should definitely switch in this case. Like you should definitely switch if some weird game show, if you're on some weird game show and this happens. Which by the way is actually based on a real game show. Monty Hall was an actual game show in like the 1970s.
Those.
So does everyone understand this? Or so should we move on to 5 doors?
Sorry if my explanation is kind of weird. But at the end of the day, it's just saying that the remaining doors that you didn't click on will always have a higher chance of having, or higher probability there will be a banana behind them than the one door that you originally select. So that's why you should always switch.
So why don't we move on to 5 doors and reveal 3? So
I just reviewed a banana.
well, actually it gets randomized every time. So every time I press the green flag, it gets randomized. So it's actually but so do you guys want to see, or do you guys want to experiment, or do you think you can figure out what the probability is just right?
Neat coding.
Sorry, sorry, Kimmy, what?
Very neat coding. This is actually quite fun to play.
Yeah. I'll definitely leave the project in the Discord server and at the end of the Zoom meeting, so you guys can all go play with this yourself.
Could you send the Discord server again? Because I did not have enough time to join that.
Oh, it's okay. I'll send it at the end of class today, so we
Okay.
can so you can stick around for a bit longer, if you
You
want to join.
Link to join.
Oh, okay. Yeah. Okay. But anyway, so let's get back. Let's not go on a tangent. Let's get back into the Monty Hall problem, or the 5-door Monty Hall problem. So does anyone think they know what the probability of? Oh yeah, and by the way, for this, it is revealed 3 doors, and does anyone know what they think the probability of getting a banana is if they switch for 5 doors? Or do you want to do an experiment to see what it is?
Probably 80%, I think.
Kimmy, yeah. So why do you think it's 80%?
Because like you have to use math. Like five. There's 5 doors divided by 100, which is 50, which is 20 for each door. There's a 20% of getting a first try. Because then since 4 doors, maybe 4 doors, probably 4 doors. We know that 4 doors are gonna be poop. So we can do 4 times 2, which is going to be 8. So 80 is the percentage.
Yeah, so can you explain like why you thought that it was a sort of, I guess, like a 1/5 or 4/5 chance of getting these doors in the first place?
Because like there's 5 doors, and we know that 4 doors are going to be poop. So probably only one of them is going to be a banana, and that's not really likely.
Yeah, so if yeah, so yeah. So if you have the other 4 doors here, that yeah, it's all concentrated into this other door that you have. All of the probability of getting the banana here is concentrated into this one door. So yeah, so
that door is being surrounded, so you know you should pick it.
okay. And we can probably see that it's probably going to be a banana. Yeah. So in this case, yeah, it is 80%. But does anyone notice a sort of pattern with the ones that we got before? So for 3 doors, it was a 2/3 chance of getting the banana if you switch. For 4 doors, it was a 3/4 chance, or a 66% to 75% to 80%. And for 5 doors, it is a 4/5 chance, or 80%.
Oh, it
Anyone
pluses
notice a pattern with
5%.
this?
It pluses 5% every time you add a door.
Not exactly.
So why don't, instead of looking at percentages, why don't we actually have a look at the fractions that they represent? So we had 2/3 before, then we had We had 2/3 for 3 doors.
What about 2 doors?
2 doors, then
Two
there
will kind of
wouldn't
defeat
really.
the point, because then if you select one, he reveals the other door, then you know for sure where the banana is.
Yeah, I mean, it is just 1/2. Yeah. Also, my program breaks if it's 2 doors, if you try to reveal a door. But as we remembered, for 3 doors, it was a 2/3 chance of getting the banana if you switched. For 4 doors, it was a 3/4 chance. And for 5 doors, it was a 4/5 chance.
Why is the 3rd door so big?
Oh, because it's it's selected if it's it becomes big if it's selected.
Okay.
Yeah, so
I
2
see that quite
3/4,
reasonable.
4/5. Does anyone see like anything that's going on there or anything interesting?
So like it's 2/3 like for a fifth. It's like going up by 1.
So you mean like 2/3? Yeah, so each number is going up from 1. So you can see that it is 2, sorry for my terrible handwriting, by the way, 2/3 to 3/4, 3/4 to 4/5. Notice how 2 becomes 3, 2, 3, 4, plus 1 on top, and 3, 4, 5, plus 1 on the bottom. So, and also, do you notice something about the bottom denominator, like the number on the bottom? How this one is for 3 doors, this one is for 4 doors, and this one is for 5 doors. Does anyone notice something about that? 3 doors, 4 doors, 5 doors.
The denominator is probably how many doors they are.
Yeah, the denominator is how many doors they are.
Yeah, so this percentage, or this fraction for the probability, shows us pretty much how we solved this problem in the first place, right? So going back to overall how we solve this for any amount of doors, you know that you only get to select one door, and then behind that one door, it'd only be 1 out of the total number of doors. So for example, if it was like 50 doors, then on your first pick, you would have a 1/50th chance of getting the banana. And then so the chance that the banana is in the other remaining doors would be 49/50, right? So for 3 doors, it'd be 2/3 chance that the banana is in the other 2. And then for 4 doors, it's 3/4, and 5 doors, 4/5. And this pattern continues.
Yeah, so that being said, does anyone see what you would think it is for 6 doors and revealing 4 doors? What you would think the chance of getting banana if you switch is for 6 doors? If we continue the pattern.
Probably 5/6.
Yeah, 5/6.
Yeah.
A lot of people in the
If
chat
we
also said
break
that.
the machine.
It doesn't go up to 6 yet.
It doesn't go up to 6 because
No more
because
space.
the
Yes, we
doors
break
would
the
go
screen,
past
so
the
there's more space.
past. Well, Scratch is kind of cumbersome, so
The doors are too big.
yeah. So
And they need a doorknob.
well, you know, cows are spheres, so we have to simplify. So if we have fit 5/6, so basically in the end, we find that if we represent the number of doors by n, then the denominator would be n, but the numerator would be n minus 1. So if n is 6 for a number of doors, 6 doors would be 5/6. 7 doors would be 6/7. 8 doors would be 7/8, and so on and so forth. 1 billion doors would be 1 billion minus 1/1,000,000,000. Yeah, so it's just
Oh
yeah.
God.
So if you
That
had
kind of looks like a billion. That kind of looks like n minus 1 divided by n.
it is n minus 1 divided by n.
That makes no sense.
And
now
n
that-
is the number of doors here.
I don't like. It looks like n divided by 1, n minus 1, and then it's divided because that's so long.
yeah, well, it actually is because if you think about it, probabilities are fractions. So division is also a type of fraction. So yeah,
Okay, yeah, true.
yeah. If we do a bit of a simplification, we would actually find that it is 1 minus. If we do a bit of simplification, we actually find that since these two cancel out, we would get like
-1.
yeah, it would be sorry, not cancel out, but they would, if we sort of separate this into an like this, n over n minus 1 over n, then we would get something like this, right? Because like when you add fractions, you just add the numerators, and since this is the same denominator, we can just separate it. So we would get 1 minus 1 over n. And does anyone well, and like we mentioned before, the chances of 1 over 1 minus 1 over n is just the chance of not getting the banana first try, and that chance gets concentrated into this last one. So this is another way to sort of think about this probability.
Cool. So does everyone get this problem?
Yes. Uh-huh.
All right, cool. So now we're gonna move on to
Wait, actually, we have a bit more with
right.
with Monty Hall problem. So why don't, instead of like before we know actually just wait 1 second, clear.
Oh god, are we gonna reveal more doors than we even have? That'll be so good.
Well, you know, that's physically impossible. You would probably break the universe simulation.
Yay.
But why don't we look instead at 4 doors, but instead of revealing 2 doors like we did previously, like this, and whoops, 2 doors, and we would have 1 left. Instead, we just reveal a single door.
That is not fun.
Yeah. What if I, yeah, so what are the chances for each of these doors? So as we remember, the original choice would obviously be 1/4. But what is the chance of any of these doors right here? Like if I choose, say, 2, what are the chances that the
35%.
banana will be inside?
35% probably. And that is not a very good scale.
Sorry, what?
It's 35%.
35%?
Yeah, there's a 1/3 of chance.
Well, you're actually really close. So as we remembered, for all 3 of these, for one of these to contain the banana is a 3/4 chance for either 2 or 3 or 4 to contain a banana. There's a 3/4 chance, as we remembered. But since we removed one of these, now that 3/4 chance is concentrated into these 2 doors. So before it was only concentrated to 1 door, but now it's concentrated into these 2 doors. And these 2 doors have an equal likelihood of having the banana behind it, right?
Yeah, but
So
why does the first door not count? The first door might be a banana too. Nobody knows.
yeah, the
Yeah,
first
so
door
that's why
might.
that's why it's a probability of getting those. So it's not guaranteed you're gonna have a better chance on those.
Yeah, the first door has a, like if we say did this about 80 times, then the first door would probably have about 20, like you would get the banana in the first door about 20 times, like generally speaking. But for these 2, it would actually be higher than 20
I
times.
think it's door 2.
It's door 2. Well, oops.
What else had to look through the doors?
But yeah, so but the thing is that if you notice the 3/4 chance in total that we have here, when it gets concentrated into these 2 doors, we can just divide that 3/4 chance by 2, right? Because there is a 3/4 chance that it is in door 2 or door 3 in this case. Does that make sense that there's a 3/4 chance that it is in either door 2 or door 3?
Yes.
Does everyone else get this?
Yeah, does everyone understand that? It is kind of confusing, but once you get it.
It's door 3. I'm
So,
so
Gavin,
sure
do you have a
it's door
question?
3.
Yes.
Oh yeah, you want to ask the question if you have one?
Yes.
Okay. What's your question?
No, I didn't have a question.
Oh, sorry about that.
Okay, sorry about that. But yeah, so if we see, then the 3/4 gets divided among 2 doors. So this 3/4 gets divided by 2. And does anyone know what 3/4 divided by 2 is? Or 75% divided by 2.
$35%.
Close?
Okay, that's pretty close.
No.
But
No, oh my god, it's undividable. Because it's an odd number divided by an even number. It's impossible.
well, why don't
make the fraction bigger? So
yeah, we can still make it a fraction. So because the 3/4 gets 3/4 divided by 2, that would just be 3/8. Or if we just look at 0.75, which is equivalent to 75%. If we just divide that by 2 in the calculator, we get 0.375, which is 37.5%.
0.375.33333. That's what you mean.
No, it's actually just 37.5. It's just 37.5. But
and I can read the doors. It's definitely door 3. For sure. What? How's that possible? You said it can't be door 1.
it could. There's always a chance that'll be door 1.
Okay.
Okay, so going back to the explanation, it's a same. So in conclusion for this, if we're only revealing one door here, it's the same concept as earlier, right? So once we choose one door, there's a 25% chance or 1/4 chance I'll get the banana. And then so there's a 3/4 chance that the banana will be in the other 3 doors that we didn't pick. Once we reveal one door, we know that 3/4 chance is in the other remaining 2 doors. So we have to divide that probability between the 2 doors. So that's what gives us
these 2 doors. So that gets 3/4.
Ooh, we broke the game.
Now for 5, if we do the same thing, it would just be 4/5 divided by 2, right? Divided by by these 2 doors, because these 4 doors probability of getting a banana gets concentrated into these 2 doors, right? So it would be 4/5 divided by 2, which is just 2/5, right? So this is yeah, this is slightly complicated, but I think it is quite interesting.
Could we do one door? Does it work with one door? Like, no, I mean, like, we have 5 doors, but we only reveal one.
Yeah, if we only reveal a single door, then this 4/5 probability of these gets concentrated into these 3 doors. So we would get 4/5 divided by 3, which is 4/15. Yeah. Yeah, it is kind of complicated, but yeah, I think you guys should like sort of think about this on your own time, but we will talk about another very interesting problem, which is chameleon.
Chameleon. Okay.
Chameleon,
Is that an
not
animal?
Yeah, so
yeah,
we're gonna
the
end with
animal.
this little puzzle.
Yeah, it's
What?
another very interesting puzzle.
So we're gonna catch one and then try to play with it?
No, we're gonna get them to change color.
Yeah, because chameleons, they are the best at camouflage, and they really like to change color.
All right, 1 second. Okay, so here's the game. This is a Chameleon Island. So there are chameleons here. So the goal is to get them to change color. So we can first go over, so there's 8 chameleons here. We can change that. So we're gonna go over like some puzzles with this. So first we're gonna explain how they change colors. So basically, if a chameleon is with a chameleon that's opposite its color, they will swap. And if 2 chameleons that are next to each other have the same color, they will both switch colors. So basically here, we can rotate these chameleons. So you can change forward 5. So they had different colors originally, so now they would switch, right? So now if we select chameleon 3 and 4, since they have the same color, they'll go to blue. Does everyone get that? So that's how...
Do you want all of them to turn
Yeah.
blue?
Sorry, what?
Do you want all of them to turn blue?
Yeah, so that's the first challenge. So how do you think it's possible to make them all turn blue?
Definitely.
Yeah, I think so.
Okay, so how do we go around doing that?
I think I know.
All right, cool. You want to give it a shot? So yeah, like which one should I change here?
1 and 2 switch. And then 2 and 3 switch. 3 and 4 switch. No, 4 and 5. Okay, never mind. I don't want that.
Oh, it's okay. Yeah. We'll not count that one move. It's okay.
4 and 5 switch.
You sure about that one? We can use a similar pattern with how you did the first 4.
No, I got that. I think I don't want that move. It just looks weird. It doesn't look right. 6 and 5, 5 and 6 change. 6 and 7 change.
There you go. So that was really like 6 moves, not 8. So yeah, so this is definitely doable with 8, and then because we can change it to blue, we can also change it to red here. It'd be pretty similar, right? So let's go to move on to 9 chameleons. Do you guys think this is possible?
Are we going to change it to the same color?
Yeah, changing all of them to the same color. It doesn't matter if it's blue or red.
No.
Okay.
It is possible, I think.
Okay, so Gavin says no.
It's not possible. It's not possible because there's one extra chameleon that's just going to mess everything up.
Yeah, so you want to... Yeah, I'll give it a shot first. So if we change everything to blue using the same strategies last time, we'll find that we end up with one extra chameleon here, like Kimi said, and then that will mess up the pattern for everything.
It's totally impossible.
I know what to do.
Yeah.
Kick that chameleon out of the screen.
Yeah, so basically we can do this. We can change them all to the same color if there's even number of chameleons, right? All right, cool. So now let's move on to something a little bit more complicated. So this is for 3 chameleons. Let's go over how they change colors. So if we have 3 different colored chameleons, they'll all change to, wait, no, sorry, this is for 4 colors. There you go. So 2 different colored chameleons. So this is for 3 chameleons. If there are 2 different colored ones, they'll change to the 3rd color. And there are 2 chameleons of the same color, they'll change to the 2 other colors. So this is a bit more complicated. Does everyone get this?
Maybe.
Maybe? Okay. We'll give it a try first and see if that improves your understanding. So we have oh.
remove the bottom ones.
There you go. Okay.
What?
So do you guys want to give this a try?
Ooh, I think I can do it. This
Yes,
is
it's
just
a bit more
weird.
complicated. They're not in a straight line.
Drag 5 out. Drag 2 out.
Okay, here.
Yeah. Yeah, and it gives it 10. Are we supposed to change it to the same color?
Yeah, whatever color you guys want.
Do it again.
So you want to do,
like drag red out and then put blue in.
so give us all yellow.
Yeah. And then do that again.
Okay, we're running out of blue.
I know. Wait, do we have one more blue or is that
Oh,
all?
we have no more blue.
Okay, red and yellow.
So that actually gives her blue, and then
Red and yellow again. Red and yellow again. And then yellow and red. Yellow and blue. Yellow and blue. And I think yellow and blue. Wait, no. I want blue and red.
So what color are you trying to change them all to?
Yellow.
Yeah. Okay.
I want blue and red because they have exactly the same amount.
There you go. So you figured it out, right? If we get the other two colors to the same number on the bottom, then we can just keep putting them together to get the same color, right? Cool. So we're going to go over the same things with the three colors. So we had 15 this time. So if we change it to 16 chameleons.
Oh no. Wait.
Oh, all right, wait. Technical difficulties.
0 chameleons left.
So we'll go over a few puzzles. So we had 15 there. So we're gonna try to find like a pattern for what we can do for the numbers of the chameleons to get them to
Oh no.
So do you guys, well, kind of said earlier, but can you guys think of a what was it? Combination of colors for the. So what is our main strategy for getting them all the same color?
Getting two colors to one color so that most of them are in one color, and then with the remaining colors we do it again till there's two colors that are exactly the same.
Yeah, so do you guys feel like it's doable this? Does anyone else want to give it a try?
This is tough.
Anyone else want to give this a try? For balancing these out?
Could we do one chameleon each? Is that impossible?
Well, let's give it a try. So do you guys think this is possible?
Probably not, because like if we put two chameleons together. Oh, this is just too easy.
What was the strategy that we used earlier, right? So this already works out for us, right?
Oh yeah, I was thinking of an impossible one.
Yeah, but like if we have any two, right, then they'll come out to make the third color, and that's correct. So now that we know the main pattern, let's go back to, I think 15 chameleons is a good number. And let's try to figure out. pattern.
We just did 15.
I thought we just.
Oh yeah, but we're gonna change the number of each chameleon here at the starting.
Ooh.
So what do you guys feel about this one? How are we doing?
Possible.
56, okay. So this is probably the last one we're gonna do before we end the session for today.
It's impossible.
Maybe try combining red and yellow together, like 4 times.
This should all work out, right? So we keep on going like this, we can follow the same pattern. So what can we do that will make sure that we cannot get a pattern of these from the starting values? We want to make sure that we can't get one of these numbers. So
I get it. 3 on blue.
3 on blue.
Yeah. 9 on red. I mean 7 on red. Okay, 9 on red. Yeah, 7 on red. And then the 5 more. I mean the rest is a rest on yellow.
Like this.
Yeah. Then we can't really like start out that normal thing. We just gotta go through a bunch of loops.
Yeah, so you guys think this is impossible?
No, because we just did it.
Oh, the 375. Wait, did we already do this?
Yeah, we did 15 chameleons, so that's probably possible.
Oh no, we changed the number of starting chameleons, like for each color though.
Yeah, but that still makes up 15 chameleons, which means we can still do it.
Oh, okay, so how we do this then?
Yellow with red. Yellow with red again. Yellow with red again. And then that's the way till yellow disappears. Yellow and red. Yellow and red. And then red and blue.
So what's your strategy here?
We're just gonna go through the same thing we did with the 15 last time, and we're just gonna make it so that we can have equal on both amounts.
Mhm.
Red and blue. Red and yellow.
Now.
Red and yellow.
Oh, you can't do red now.
I mean yellow and blue. Yellow and blue. Yellow and blue.
We reached the same problem as earlier. We run out of the yellow if we keep going like this.
Wait a minute. I'm thinking. This is probably impossible.
Does anyone else have a guess for why this is possible? Starting colors. We had 3, 7, and 5 this time. So those were starting numbers.
3, 7, and 5 are all odd numbers.
Think that's a reasonable guess here? Yeah, that could be the reason, but the main thing is that they're all separated so that we're not able to get the thing where they're all balanced out here.
What if we do 3, 4, and 5?
Yeah,
Would
anyone
that
else want to give a guess for this? We can also try 3, 4, and 5.
Because like that is reasonable. It's probably impossible. Because last time we did it and it did not work. For 3, 7, and 5.
Do you think because we have an even number here now it'll work?
I don't think so, because we can't really make up anything.
Yeah, so if we're not able to, because it's the only way we can increase the numbers of the other one is by adding 2. So if they're not separated like that, it's not possible. Does everyone sort of get this? Okay, yeah. It's 8 o'clock, so we'll have some more discussion problems about the chameleons because this is pretty interesting this week.
Okay.
Yeah. I don't want to go over time too much, so yeah, you guys are welcome to leave, or you can stick around a little bit longer if you want.
Thank you.